Ionization energy is the minimum energy needed to remove an electron from an atom or ion. If we start with a generic atom, call it M, and we put the right amount of energy in, what we can do is knock an electron out of that atom and turn it into an ion. If we have, as you can see on the right side of the screen here, I've tried to represent this as a cloud of electrons, and there is buried in the middle right there a nucleus. If we add the right amount of energy, we can knock an electron out of this cloud. The second ionization energy is the energy required to remove the second electron, and the third ionization energy is the energy required to remove the third electron, and so on. Successive ionization energies are larger than previous ones, and this is because the positive attractive force remains the same, but there's less electron-electron repulsion. In other words, if you look at this cloud of electrons that I've represented on the right side here, you can think of those electrons being where they are because there is a balance between the pull from the nucleus that tends to hold the electrons in and the repelling tendency of all of these other electrons. Well, once I've taken one electron out of there, the amount of pull on each electron from the nucleus is the same, but the amount of repelling from the other electrons is less because there are fewer electrons. Therefore, if I want to knock, say, the second electron out, I've got that species with more energy than it took to remove the first electron. The ionization energy increases sharply when we try to remove an inner shell electron. Here are the first three ionization energies of magnesium. Magnesium, as you recall from the periodic table, has only 2 valence electrons. And we can see from these energies that the second ionization energy is about 2 times as big as the first ionization energy. And then the third ionization energy is more than 10 times the first. This is very strong evidence that in the case of magnesium specifically, and in the case of all other elements generally, that only the valence electrons are involved in bonding. The energy price that must be paid if the core or kernel electrons are involved in chemical bonding is simply too high. Now, as we go down a group, the first ionization energy decreases. And here's why. The effective nuclear charge on the outer valence electrons stays the same as you go down a group, but there's more screening, that is, there's more electron-electron repulsion. Let's use an example here with lithium and potassium, both alkali metals. You can see that I've represented the single valence electron off to the right of each of these atoms, and I've represented the core or the kernel electrons with dots and a shield. And you can see that with potassium, the shield is much, much more elaborate. In other words, there's a lot more negative charge here than there is in the case of the lithium. Now, let's calculate the effective nuclear charge on this valence electron and that valence electron. For lithium, we go number of protons minus the number of electrons between the nucleus and the electron we're interested in, so 3 minus 2 is 1. For potassium, 19 protons minus 18 electrons, core electrons, gives you 1. So these have the same effective nuclear charge on the valence electrons. In other words, the pull of the nucleus on these valence electrons is comparatively similar. But the screen for potassium is much more strong. In other words, all of this negative charge here tends to repel potassium's valence electron much more strongly than this tiny screen tends to repel lithium's valence electron. Therefore, it's much easier to remove the valence electron from potassium, which is why we said in this statement here that as we go down a group, the first ionization energy decreases. Generally, as we go from left to right, the first ionization energy increases. Think of, say, the third period in the periodic table. sodium is on the far left, it's very easy to remove one electron. If you go all the way over in the third period from sodium, on the far right of the third period you get argon, and argon doesn't want to lose any electrons, so even to take one away is going to be very difficult. So as we go from left to right, the first ionization energy tends to increase. Now there are a few exceptions. For example, the first ionization energy for boron is actually less than that for beryllium, even though boron is further to the right. And this is because boron doesn't like to have that single electron in its 2p subshell. So it makes it very easy to remove that 2p electron. Similarly with nitrogen and oxygen, they have these electron configurations. If we were to draw out an orbital type diagram for nitrogen, we would see that the 2p orbitals would go up, 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 3 electrons in the 2p orbitals. For oxygen, we would have to go up, 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 down. That's 4 electrons in the 2p orbitals, and it's much easier to remove that electron than it is any of these. If we want to summarize this, here's how we're going to do it. We're going to say that subshells prefer to be either completely filled or half filled. In the case of boron, we've got kind of a spare electron here just dangling in the 2p orbitals, so boron makes it a little bit easier to knock that baby out. Similarly, down here with oxygen, we've got this 4th electron that's, pardon the expression, acting like a 5th wheel, and it makes it a little bit easier for us to knock that one out. Subshells prefer to be either completely filled or half filled. So here's a diagram that shows the general trends we're after. As we go down a group, for example the noble gases, there's helium and neon and argon, you can see that as you go down a group, the first ionization energy decreases. As you go across a period, you can see that in general, the first ionization energy increases, except there are a few exceptions, from beryllium to boron, from nitrogen to oxygen, and in the elements below those, in the next period, magnesium to aluminum and phosphorus to sulfur.